Swayam Prabha. Digital India. Educated India.
So, hello everyone. So, we will discuss our next topic, which is variance length curve. So, we have discussed the diagram related to unevenness in yarn, then how to locate the defective roller. For that, we have discussed the spectrogram. Now, another concept, which is variance length curve. So, we see that for any yarn, variance length curve normally we use for yarn. So, I will give reference only for the yarn. We can also make we can get the variance length curve for roving and sliver also, but here at present I will give reference to only yarn for our better understanding. Now, this is the typical mass variation curve. Okay. Now, what we see, suppose this is total length of yarn tested is L. L is the total length of yarn tested. Here we are cutting the length, total length, into say two equal parts. Two equal parts. Initially the total length is L and mass is say M. So, as we are taking total whole length, so there is no variability. We cannot get any variability within it. So, we will get one mass per say total length. So, M mass per total length will be, because we have only one data. Now, if we take say two components, say equally we are dividing, so this is the say L1, L2, and we are taking mass say M1, M2, two components. Here what is happening? Here whatever variability within this length, so A, B, C, total length of yarn say AC. So, within AB length, total variability is actually which we are not getting. We are getting only the mean value of mass, it's M1. Similarly, the other components, so BC, we are getting the mean value M2. But we can get the variability between M1 and M2. Okay. Similar way, if we consider here that variability here, we are taking the length, smaller length. So, we are taking the mass of this point, we are cutting it to very small length, very small length we are cutting. So, length is say 1 millimeter cut length, imaginary. We are taking cut length of say 1 millimeter, very small cut length, and we are taking mass W1, W2, W3, W4. So mass at every point we are getting, and then we are calculating the standard deviation. Then from there we are calculating the mean, then calculating the CV percent, and then calculating the relative variance or variance. Okay, and this variance for a cut length of 1 millimeter is plotted in a XY plot, XY, where X axis it's a cut length and Y axis being it's a variance, which is CV percent. Y axis is variance, and we have plotted. So let us see, 1 millimeter is the minimum possible at our present situation. So this is 1 millimeter we are cutting. We have taken mass, although 1 millimeter of yarn weighing that value, it will be difficult, but let us imagine. And we have got a variance value we have plotted. This is the variance value with 1 millimeter cut length. Now what we have done, next time we are not taking 1 millimeter cut. We are taking a say 1 centimeter cut length. This is 1 centimeter, this is 1 centimeter, this is next 1 centimeter. We are getting next plot, we are getting cutting 1 centimeter, 1 centimeter cut length next time. So this will become M1, M2, M3 in this way. And we are calculating standard deviation again, CV percent and variance for each 1 centimeter cut length. Although this mass will be more than 1 millimeter cut length, but here in 1 centimeter we are actually averaging out the variability within that. We are not taking into consideration of variability within 1 centimeter. So the M1, M2, M3, after averaging the 10 1 millimeter pieces, so we are getting the average value of this. So as the variability within that 1 centimeter is averaged out, so this variability, the variance will be less than, so this will be variance 2, earlier it was variance 1. So this is a variance 1 earlier for 1 millimeter. For 1 centimeter, the variance value V2 will be less than V1. So here we are putting variance V2. With the same process, if we take say 1 meter cut, this will be further reduced V3 for 1 meter cut. In this way, if we go on increasing the cut length, you will get the variance gradually V4, V5, gradually variance will reduce. And what we are getting here, the variance between these cut lengths. Earlier variance between 1 millimeter cut length, second time variance between say 1 centimeter cut length, then variance between 1 meter cut length, means between the pieces each of 1 meter, 1 centimeter. So as it is between the small pieces, variance between the small pieces, cut length in x-axis, and y-axis, it's a variance between cut length. So that's why it's between cut length, and in short it is termed as BL, and the shape of the curve is this. This is the shape of the BL curve. It's not, just let me draw shape of the BL curve is this. Okay, between length, you can see here. So mass of each length L is measured and CB is calculated. Okay, L, then L varies subsequently. So L we are changing. L initially 1 millimeter, then say 10 millimeter, 1 centimeter, 10 millimeter, 1 meter, in this way. And this CB percent is the CB between say 1 yard length. So 1 yard length is given the symbol. So this is the L yard. So CB L. So at variance length, so between length L. So this is the shape, and the point where it is become 0, as we have discussed, this is the total length tested. When it's a total length tested, that means you have only one data, so variance will be 0. Okay. And next is the within length. Again, going back to the same plot, variation plot, mass variation plot. Here, if we see here within length, now if we take very small length, now this variation, let us try to discuss with the actual figure of yarn. This is the actual. Now if we take a very small portion of yarn, very small, say 1 millimeter portion, 1 millimeter portion, and try to get the variability within 1 millimeter. So this 1 millimeter, this is, although it's a very uneven yarn, but if we take the small cut, this is small cut portion, and this is say 1 millimeter, 1 millimeter, and now imagine 1 millimeter we are again subdividing into say 100 small pieces, very very small pieces. In 1 millimeter cut length, and we are trying to get the variability within that, within 1 millimeter by some means. We are trying to calculate the variability within 1 millimeter. We will see variability within 1 millimeter is least. If the cut length, imaginary cut length is 0, then the variability within that length will be 0. Okay. Now, if we gradually increase the cut length, so initially 1 millimeter, now we are making it say 1 centimeter cut length. In 1 centimeter cut length, we will see we are taking into account some of the variabilities. So at certain, there will be variability, and if we calculate the variance, standard deviation, coefficient of variation, and then variance, we will get little bit higher variability. So in this way, if we go on increasing the cut length, we will actually accommodate more and more variability within that portion. So we are gradually increasing the cut length, and will incorporate all the variability if we take the cut length as total yarn. This is the total yarn. So total variability will get if we take the cut length as whole cut length. This is called CV within length, variance within length. So it's expressed in terms of VL. Within length is expressed in terms of VL, and between length is in terms of PL. And if we take a particular cut length, say particular cut length, and if we add the variance between length and variance, sorry, between length and variance within length, we will get the variance, total variance, VT. And at any cut length, the summation between BL and VL is constant. That is total variance is the summation of BL and VL. This we have discussed. CVL or CV of these are the shapes. This is BL and this one is VL. Total variance is summation of BL and VL. Now try to solve some numerical, okay? And one thing is that this shape of BL curve or VL curve, they are typically follows logarithmic scale, okay? And if we plot the x-axis cut length in log scale, log of cut length, then the typical BL curve will be straight line for an ideal yarn, and for a defective yarn the BL curve will deviate little bit at the point where the particular periodicity is there, okay? Now let us see the numerical. The nature of BL curve of yarn is y equal to mx plus c, where y is the variance square of CV% and x is the log of cut length, okay? So this is the log cut length and this is the variance, and the shape as I have discussed, this is the variance line. Here it's a y equal to mx plus c and c is a constant, okay? M and c are constant. The variance within 10 centimeter and 1 meter cut length are 40 and 20 respectively. What will be the approximate U% that yarn tester, evenness tester will test? So U% we know the capacitance type tester where cut length is 1 centimeter. Why it is 1 centimeter? Because the capacitor plate length is 1 centimeter, as this we have discussed. Now if we solve this numerical, these two equation, this is the variance and variance are given, this is the variance is 41st for first yarn with a 10 centimeter cut length, 40 is the variance, M is constant, log 10 and C, and log 10 means 1, so M plus C is 40. This is one equation, and next is for 20 that's the for variance 20 we get at 1 meter cut length, so 100 centimeter, so it will become 2m plus c. So these two relationship if we solve we will get the values of M and C. So M we get, M is the slope of the curve minus 20, and C we get 60. And in Worcester evenness tester, the card length is 1 centimeter. So variance will be minus 20 m, and card length is 1 centimeter plus 60, C is 60. So this will become, this first part will become 0, log 1 equal to 0. So it will be, variance will be 60. So variance is nothing but CV square. So we get the CV value under root 60, 7.76%, and from the relationship U percent equal to PMD, percent mean deviation, and the relationship between percent mean deviation and CV, from that we can calculate the CV percent divided by 1.25, it will be 6.19%. So in this numerical we solve the equations, and then whatever we are getting CV percent, that the relationship between percent mean deviation and CV we are using. So this percent mean deviation which we are getting, so the value 6.19 will be approximately the U percent which we will get in the instrument. The next numerical, a similar numerical here. Here it is given that what will be the count CV. So we measure the count CV based on 120 yards of length. Okay, we take the cut length as 120 yard and then measure the count CV. Now here in the PL curve, at 1 centimeter and 1 meter cut length, so this is the PL curve. At 1 centimeter cut length and 1 meter cut length, the variance here is 54 and 26. This is 26. Variance 26, here variance 54. Because this is y equal to mx plus c, it will be straight line. And using these two relationships, one is 54 variance log 10 log 1, so this will become 0 because it's 1 centimeter. So here C value is 54, and similarly next equation is 26 equal to 2m plus C. So from there we can calculate the value of m. So m becomes minus 14 and C is 54, and in a similar way we can calculate the CV percent at 120 yards. So card length. So 120 yard, if we convert, it becomes 10,972.8 centimeter. And then using that length, cut length here, using the equation and replacing the constants m and c, we get CV square, this is not CV2, this will be CV square, it will become 6.58 and CV percent will be under root 6.58, it will be 2.56%. So in count testing, if we take Lee of 120 yard and if we test, we will get a count CV of 2.56. Okay. Next, similar numerical with certain variation in data. So variance with 10 centimeter and 1 meter cut length, we are getting 50 and 34 respectively. So we have to calculate the count CV. In the similar way, we will solve this numerical. So y equal to mx plus c, from the given relationship, 50 is the variance in the first case where 10 centimeter cut length was there. So the m plus c will be 50, and then for the next situation where 34 was the, this is 34 was the variance and cut length was 1 meter, that is 100 centimeter. So we get 2m plus c equal to 34. So if we solve this two equations, so we will get m value minus 16 and c 66. Again, the cut length for 120 yard is that for 120 yard it becomes 10,972.8. We have already seen, we have done earlier numerical. From there, variance is calculated 1.35 and CV percent is 1. Under root of 1.35, it will be 1.62. Under root 1.35 is, what is the under root of 1.35? 1.16. This is actually, it will be 1.16%. Okay, this was wrong. So 1.16%. So we can get the count CV also. You can actually, without measuring the count CV, from the variance length curve, we can calculate. This will become 1.16. So this is wrong. So it will become 1.16. Okay. Next one. The nature of BL curve, again similar BL curve, and where M and C are constant, the variance with 10 centimeter and 1 meter cut length 63 and 37 respectively, what will be the approximate U percent? So the same problem we have done. So let us do it quickly. So 63 is the variance where 10 centimeter is the cut length, 36 when variance is 36, 1 meter cut length 100 centimeter. From by solving this relationship, so M value we are getting minus 27 and C we are getting 90. So in Worcester evenness tester, cut length is 1 centimeter cut length. So variance is 90. So CB% we can calculate, it's 9.48, that's under root 90, and from there percent mean deviation we can calculate U%. CB divided by 1.25, it will be 7.58. Okay. Now next analysis is, it's a deviation rate. So deviation rate is another forms of representation, and it will give the numerical value. So if we see the deviation rate, which is calculated based on certain relationship. So what is that? Suppose this is the mass deviation curve. Mass deviation curve is given, and we have set one particular range. X1 is the, X bar is the mean mass per unit length, and we have set certain plus minus certain distance, certain value. So X bar plus minus say 2 or any other value, or X plus minus 2% of X bar. So 2% variation. Okay. The range which we have selected for a particular variability. So X bar is the mean plus minus say 2% of X bar. The 2% variability we are trying to see. So this is in the higher side and this one in the lower side. And then we are plotting, and this zone is actually exceeding the limit. So this green shaded zones are exceeding the limit. Okay. Now we calculate or we measure the length of the yarn which is exceeding that limit, and total length of yarn we calculate. So here total length of yarn which is exceeding the set limit is D1 plus D2 plus D3 plus D4. So D1 is the total length, D2, D3. So this D1, D2, D3, D4 are the total length of the yarn which is exceeding the set length, and if we divide by the total test length L, total test length, that gives the, if we measure in terms of percentage, that gives the value dr%. So what it's giving, so as we have discussed, higher diameter means higher mass per unit length is actually corresponds to higher diameter. So this yarns, these portions will be thinner and other portion will be thicker. So this will give one value, numerical value, which will represent the visual appearance. So The higher this DR percent, that means deviation rate percent, it will give us the indication that okay, this particular yarn is giving some higher thick thin places or higher variability. So DR means deviation rate. Okay. So it indicates the ratio of the total length of irregularities. So ratio of total length of irregularities, the total length, the D1, D2, D3, D4 ratio with the total length. It's determined on the basis of the yarn irregularity signal averaged over certain length, small reference length, that is, this is a small reference length, which exceeds the preset level. So preset level we are exceeding, and to the total measured length. So this is preset limit we have decided, as in our case we decided plus minus 2%, and total length, the ratio is there. So it shows the correlation with the evaluation by naked eye, that is appearance of the fabric. So it is actually gives the it's giving the numerical value which we will get the appearance, actual appearance in the fabric. Now apart from the capacitance type tester we have discussed, there is a photoelectric type principles are there. So here we can see the animation. Light source is going through a lens and it's projected on a slit, okay, through which the yarn will pass. So yarn is passing, and depending on the yarn diameter, we can get a plot. The yarn will move across, we will get a plot which will give the diameter variability. So photoelectric method, it gives the variability in terms of diameter. So this is the principle is different from the capacitance type method, where in capacitance method we get the variability in mass per unit. Okay. So here we can plot the curve, the variability in diameter. So this indicator, it's reflected. So we can plot the variability as yarn moves through the sensor. Here this is given. Now another method is optical method, which is infrared sensor is there. So I will show the method. So optical method determines the yarn diameter and its variation, and it works on IR transmittance method. Yarn passes through the beam, one of the beams, and block the light. So there will be two identical receivers will be there, and the reference receiver, the intensity is compared with the other receiver, and we can get the variability in yarn diameter. So optical method is claimed to be nearer to the human eyes. Obviously, because it measures the difference in diameter, variability in diameter. Okay. Now you can see the principle here. This is light source. IR beams are equal, two equal beams are projected. One is the reference beam, another is through the yarn. Okay. And reference beam, the difference between the reference beam intensity and the other receiver is a measure of the yarn diameter. As the yarn moves, we get the plot continuously, and it's connected with the computer. The intensity is received by two receivers are processed in the computer. Okay. Now we have reached almost in the last segment of the yarn evenness testing, and which is the fault classification. Now what we have discussed earlier, the irregularities are there in the yarn, the thick, thin naps, okay, thick thin naps, they are the inherent part of the yarn. Thick thin naps will be there, they are the inherent parts of the yarn. They cannot be separated, and they generate due to the actually unavoidable faults. That means fiber type of fiber defects, or maybe due to the drafting fault, or maybe due to the carding, some thick portion is generated. Okay, and this cannot be separated, but they can be reduced, levels can be reduced. But apart from this type of faults, these are also faults, but they are classified as the imperfections, because to differentiate from the faults, faults are the defects which are defects with a higher intensity, which are unacceptable in most of the cases, unacceptable in nature. And the imperfections are also faults, but they are with a very lower extent, which will be there in the yarn, in the staple yarn particularly, and to some extent they are acceptable. But faults are of larger extent, and most of the faults, they are not in regular fashion. They don't generate in the regular fashion, they generate occasionally. And these faults are classified based on the reference mass per unit length with the mean mass per unit length of the yarn. Okay, and they classified based on the mass per unit length and the length of the fault. And in most of the cases, these faults are objectionable faults, and they have to be removed. So if this is the fault remains in the yarn, so this portion, it will affect the appearance of the fabric. Fabric will be rejected, unacceptable. So these faults are unacceptable. So what we normally do, we remove this fault by cutting this portion, just like an operation. Okay, we are operating on the yarn, we cut the unacceptable portion. So this is, suppose this is the yarn with one unacceptable portion, very thick portion, and what we do, we cut out this portion, remove this portion, and then we take other ends and we join. Somehow we join, and this joining is done by splicing. We use splicing, and this is done in the cone winding machine. When winding machine, after spinning, then when winding, we remove this objectionable fault. So the classification is done. So yarn imperfections which is greater than 100% of mass or longer length or both are regarded as faults. So yarn imperfections are separated with the different terms as faults. Faults means with a higher extent. So imperfections are more frequent while faults are seldom occur. So faults have greater impact on appearance and performance of yarn. So there will be breakage in weaving, like particularly in warp sheet, if the thick, very thick faults are there. So that's why we have to remove. So faults are classified in different groups based on their diameter or their mass per unit length and the length of the fault. So that we have discussed. So here we will discuss one of the classification system. So the reference we are taking, Classimat 2, where 23 categories of faults are there. This classification system has been improved subsequently. Classimat 3 and subsequent models are there, but the basic principles are same. But only difference is that their classifications are more and more classifications are used. Now you can see this is the classification of faults in faults by the Classimat 2, where we have 23 types of faults are classified. In the upper side, this is the baseline. Okay, this is the baseline of mean mass per unit length. Mean mass per unit. So in the higher upper side, those faults are thick faults, and in the lower side they are thin faults. Now these faults are classified. So 100% plus 100% plus 150 plus 250 plus 400. So between 100% and 150%, so 2 times or 2.5 times, it is classified as fault type 1. Okay, and when it's plus 150 to plus 100 250, so it's more than 150 and less than 250%, it is classified as 2. The group is 2, second group, and between 250 to 400 it's group 3, and above 400 group 4. That means the level 1 for thick portion is the extent of variation is less than the level 4 as we increase the. Similarly, for thinner side, level 1 means the thin portion between minus 30 to minus 45, and level 2 is minus 45 to minus 70. So, level 2 is thinner than level 1. So, 1 to numerical values are indicating the level of mass per unit length, and the alphabetic, these alphabets are A, B, C, D, E. These are showing the length of the fault. So, A, B, C, D means, so B is longer than A, similarly C is longer than B. In this way it will. That means what does E means? E means it's a very thick and very long faults. This is, it's a long thick faults. Okay, which is, we call it a slab, which is totally unacceptable. So A1 means, A1 means it's a thick place with a lower extent and the length of the thick place is smaller, between 0.1 to 1 centimeter smaller. But A4 is, the length of the thick place is smaller, but the extent of thickness is very high. Similarly, D4 is longer also, so 4 to 8 centimeter and very thick, more than 400%. Okay. Similarly, if we go to the longer side, the thinner side, so H1, H2. H2 is more, it's thinner than H1, and I2 is longer than H2. But between I2 and H2, the extent of the thinness are same, but I2 is more objectionable because the length of thinness is, thin portion is longer. So, if we see here in this plot, the fault D1 among A1 to D4, so fault D4 is highly objectionable because the thickness is more and the length is more. D3 is also objectionable, but its thickness is less than D4. In this way, so we can identify the objectionable fault. So this is C4 is objectionable because it's very thick and length is also little bit higher. Now the short thick faults are A4, B4, C3, C4, D3, D4. Okay. These are objectionable faults. These all are objectionable faults. These faults should be removed from the yarn. Although the frequency of the very thick faults are definitely lower, so we have to remove, we have to stop the machine, cut the portion and remove it. Similarly, shorter norms, there's a stricter norm. In the stricter norms, if we want to be very strict, we want very clean yarn. So A3, B3, C2, D2, this can also be removed. And long thick faults, E and G, they are long thick faults. This can also be removed. And thin faults are H2, I2, I1. They are also thin faults which can be removed. So these thin faults actually result the breakage in the yarn during the weaving and also the thin line in the fabric. So during the winding, we can set the cutter setting based on certain curve. So where we want to remove the faults, so the shaded area, if we want to remove this type of faults, so we can set our cutter, and then as soon as the type of faults will reach within the cutter zone sensor, the cutter will cut that portion and then splicing will act. Okay. So these are all about our discussion on yarn evenness or evenness of fibrous material. Thank you. So next class we will discuss and some different topics, which is we'll discuss the transmission characteristics. Thank you.